When we observe a chemical reaction with the naked eye, it often looks like a chaotic explosion or a spontaneous transformation of matter. The reality is much more rigorous. These reactions are highly disciplined, mechanical transfers of specific atomic components. To understand how substances alter their physical identity, we must stop looking at the macroscopic change and start tracking the movement of individual atoms. Chemists use a precise framework called oxidation and reduction, commonly known as redox, to map exactly where these atoms travel. Mastering redox reveals the invisible rules governing everything from rusting metal to the cellular metabolism keeping the human body alive. To uncover the mechanics of redox, we will bypass simple examples and immediately deconstruct a fully balanced multi-reactant system. This equation represents the specific reaction between solid iron and water vapor that produces iron oxide and hydrogen gas. It is a map showing a before and after state of atomic architecture. By tracking the precise pathways of the oxygen and hydrogen atoms across this divide, we will reveal the dual mechanisms of oxidation and reduction. We begin our deconstruction on the left side of the equation. Each chemical equation functions as a direct record of atomic movement. Looking at the reactant side, we isolate and observe only the iron. Before the reaction begins, this iron exists in a pure, isolated state. Directing our attention across the arrow to the product side, we locate what it has become. In this after state, the iron has physically bonded with oxygen atoms to form an entirely new lattice, iron oxide. This provides the first foundational rule of the framework. When a substance mechanically gains oxygen during a reaction, it has undergone oxidation. In this specific system, the iron is the entity that has been oxidized. Oxidation identifies the literal, measurable addition of oxygen atoms to a target structure. We shift focus back to the reactant side, isolating the water molecules. Notice they enter the system with oxygen securely bonded to hydrogen. Look to the right side to see the fate of that hydrogen. To form this pure hydrogen gas, the water molecules had to be violently stripped of their oxygen payload. This establishes the second foundational rule. When a substance loses oxygen atoms, it undergoes reduction. The water, having its oxygen forcibly removed, is the reduced actor in this chemical narrative. This raises a critical question. Where did the oxygen that bonded with the iron come from? And where did the oxygen stripped from the water go? Atoms do not materialize from the void, nor do they vanish into nothingness. As this conceptual ledger shows, the oxygen gained by the iron is the exact same oxygen lost by the water. The oxidation of the iron was entirely mechanically dependent on the reduction of the water. This principle of simultaneity is exactly why the scientific community combines the terms into the portmanteau redox for reduction-oxidation. You can never have one without the other. They are a single, synchronized transaction. Every chemical system operates on a strict zero-sum economy, where one molecule's loss is strictly dictated by another's gain. Defining redox solely by the movement of oxygen describes only one aspect of these transactions. We observe the second half of the framework in the combustion of methane. Look at the carbon in the methane on the reactant side, surrounded by 4 hydrogen atoms. Tracking carbon to the product side, it loses its hydrogen while simultaneously bonding with oxygen. Because this carbon atom bonded with oxygen while shedding its hydrogen, the loss of hydrogen is also classified as oxidation. Now, track the raw oxygen gas from the reactant side to the product side, where it gained those exact hydrogen atoms to become water. Conversely, because the oxygen gas gained hydrogen to reach its product state, the gain of hydrogen is defined as reduction. Whether we are tracking the addition of oxygen or the subtraction of hydrogen, the core mechanics of a redox transaction remain identical. Keeping track of gains and losses across 2 different elements can feel disorienting. To manage this, chemists organize these rules into an inversely mirrored framework. On the left side, oxidation is defined as the gain of oxygen or loss of hydrogen. On the right side, reduction is the exact inverse, the loss of oxygen or gain of hydrogen. Applying this matrix allows for the systematic analysis of almost any standard chemical reaction. This framework serves as the primary tool for tracking shifts in atomic identity. Because these transfers are strictly physical processes, chemical equations are not just theories. They must always obey an absolute, perfect mathematical balance. Re-examining the hero iron equation and the methane equation side by side, we draw our attention to the large numbers placed before the molecules. These coefficients, like the 3 in 3Fe or the 4 in 4H2O, are not arbitrary suggestions. They represent the strict mathematical ledger required to make the transfer work. Creating iron oxide strictly demands the oxygen from exactly 4 water molecules. This numerical balancing proves the conservation of mass. No atoms were destroyed, and no atoms were created out of nothing. Every single atom oxidized by one element is perfectly accounted for by the reduction of another. The chemical equation remains a flawless accounting ledger, proving the absolute balance of the physical universe.